In this video, I'm going to talk about internal stability for linear time invariant system. So in the previous video, I talked about the BIBO stability, which is also the input and output stability for linear time invariant system. So for the internal stability for linear time invariant system, we typically assume that we have a zero input, which means if I give you a linear time invariant system, which is given by x dot t is axt plus but, yt is cxt plus dut. So here ut is assumed to be 0, which means we have 0 input. So the internal stability talks about the property for a linear time invariant system given initial condition x0 to see what kind of property we have. So in terms of the definition of internal stability, we have two types of stability we're talking about. One is called marginal stability. One is called asymptotic stability. So here's the definition of the marginal stability. So for the linear time invariant system with a zero input, given as a star in the beginning of this page. So if the initial condition is bounded by a certain value, for example, the normal x0 is less than or equal to xm, which is a positive number. If this one means that my output of the system, which is y sub t, is also bounded by a certain number, a certain value, which is y sub m, the system is marginally stable. This is also equivalent to say if the initial condition x0 is bounded implies that xt is bounded. So all the future states are bounded. That's because my c is constant. So if xt is bounded, so my y sub t will be bounded. So we don't have to actually analyze y sub t. We just need to analyze x sub t to see if it's bounded or not. If x sub t is bounded, because c is a constant, so my y sub t will definitely be bounded. So that means if x sub 0 is bounded initially, which implies that x sub t is bounded for any future time t, then we call the system is marginally stable. So they are equivalent. This is because, as mentioned before, y sub t is equal to cxt. So a bounded of xt will mean a bounded y sub t. So this is the definition of marginally stable. Okay. So as we mentioned in the previous, for the BIBO stability, we want to know what kind of condition will guarantee the internal stability. Okay, so as mentioned before, so we don't look at the we don't need to look at the y sub t. Instead, we only need to look at the y sub x of t by having a zero control input u sub t. So the system becomes just x dot t is equal to axt, because we don't have to look at the y sub t, and we don't need to we have a zero control input u sub t. Okay, so in other words, we can say the system, the star is marginally stable if a bounded initial state excites a bounded output x sub t over here. This is also equivalent to the black one, black star, the equation represented by the black star. Okay, because they're equivalent. Because the red one, the marginal stability of red one also means the marginal stability of the black one. Okay. So here's a definition of asymptotic stability. So the red one, which is given by this one, is asymptotically stable if a bounded initial state x0 excites a bounded output x sub t, and also we have a second condition, which the first condition is the same as marginally stable. There's one actual condition to guarantee the asymptotic stability, which is this xt will go to 0 as t goes to infinity. Okay, so this is a condition to guarantee asymptotic stability. Notice here that also, even we say here the definition is based on the red one, actually it also implies the black one. This equation is asymptotic stable. Okay, again, that's because my y sub t is equal to c times x sub t. Now c is constant, so a bounded xt means a bounded y sub t. Okay, so that's the definition of the marginal stability and asymptotic stability. Okay, so now take a look at an example how we verify a system is marginally stable and asymptotically stable. Okay, For example, if I give you a system which is given by x1 dot is negative x1 and x2 dot is positive x2, okay, so this can be written in the form as written in the red star, okay, so which can be written as x1 x2 dot is equal to negative 1 0 0 1 times x1 x2, so which is the form given by the equation denoted by the red star. Okay, so here we have A is negative 1 0 0 positive 1, which is 2 by 2 matrix. So is the system marginally stable? So based on the definition, because we don't know any other condition to verify if the system is marginally stable or not, so we just need to use the definition. So definition says a bounded initial state x0 excites a bounded output x of t. So in order to verify this, we need to compute the x of t to see if it is bounded or not for a bounded initial state x0. Okay, so we just calculate the solution. Okay, so this is nothing but we calculate the solution to the two differential equations because they are decoupled. So for the first equation, x1 dot equal to negative x1, assuming we have an initial condition x1 0. Okay, so we just can find the solution. Okay, I won't go to the detail about how to solve the differential equation over here because it's really straightforward. So the solution is given by at least the steps to compute the solution, but I wouldn't talk about the details. So generally speaking, we can find the solution of x1t is given by x10 times e to the negative t. That's the solution of x1t. So similarly, I can compute the second equation is just be given by x2 dot is x2. So we'll follow the same procedure. So the difference here is the number here is a positive one, it's not a negative one. Okay, so the solution for x2t is equal to x20 times e to the t. The difference is this is positive one and this is negative one. Okay, that's the solution. So we need to verify if they are bounded. If x1, x2, they are bounded for all time t, if I have a bounded initial state x10 and x20. So as we can see from here, x10 is bounded, so this guy is bounded because e to the minus t for t is greater than 0. This is greater than, of course it's non-negative, and also it's less than or equal to 1 for any positive t. So this is bounded. Yes, x1t is bounded. This is true. This is bounded. Let's now check x2t. Okay, x20, so this is bounded because it's bounded in the initial condition. This guy is not bounded because e to the t will go to infinity as t go to infinity. Okay, so this is not bounded. So x2t is not bounded. So this is not the marginally stable. Okay, because x2t will go to 0, go to infinity as t go to infinity. Okay. So this second example, we just change this number a little bit. Let's see, we change this the second equation. Also, we don't change the first equation. We change the second. We also add a negative sign over there. So which means I have x1 dot t is equal to negative x1, x2t is equal to negative x2t. Again, we can write this one in the standard form. X dot t is equal to a times xt, right? Then we can still find a solution, which is x1t is x10 times e to the negative t, x2t is x20 times e to the negative t, which is the same, use the same way that I computed the solution to the previous example. So again, because this guy is bounded, this guy is bounded, and this guy is bounded, this guy is bounded, so yeah, essentially x1t, x2, they are bounded for all t is greater than or equal to 0. So I can say this system is marginally stable. As a matter of fact, if you verify x1t, x2t, they also go to 0 because here as t go to infinity, so as e minus t will go to 0 as t goes to infinity. So this term will go to 0, and this term again that's the same, so will go to 0 as well. So x1t and x2 they will go to 0 as t go to infinity, which means the system is also asymptotically stable. Okay. So that's the way how we can verify a system is marginally stable and asymptotically stable based on the definition. The key idea is that we try to compute the solution of xt, and to verify if this xt is bounded for all positive t as t goes to infinity. For all t for a bounded initial condition x1 x0. Okay. Now that's the definition. So here we'll talk about some of the analytical way, we can verify system is stable, meaning that can we look at some of the structure of my system, especially my matrix A, to verify if the system is stable or not. So here's the general condition that guarantees the system is marginally stable. Okay, so the linear system which is x dot t is axt is marginally stable if and only if all eigenvalues of A have 0 or negative real parts. Okay, so which means, yeah, we need to check the eigenvalues of A. The first condition is eigenvalues of A have negative 0 or negative real parts. Okay, the second condition is these eigenvalues with 0 real parts must have the same algebraic multiplicity and the geometric multiplicity. So I'll talk about the definition of these two multiplicities later on when I give an example what that really means. Okay, I just need to remember the two conditions to guarantee a linear time invariant system is marginally stable. First one, the eigenvalues of A must have 0 or negative real parts. The second one is the eigenvalues with 0 real parts must have the same algebraic multiplicity and geometric multiplicity. Okay. All right. Now let's take a look at example how we can use this condition to verify a system is marginally stable. Okay. So the first example I give you is x dot t is equal to 1 0 0 0 negative 1 0 0 0 negative 2 times xt. So we want to verify a system is marginally stable or not. Okay, so here I give you an example. This matrix is pretty straightforward. It's A, the diagonal matrix. So actually it's very easy to compute the eigenvalues. Okay, so I don't want to give a very complex example since our goal to verify these conditions. So it's better to easily find the eigenvalues. So as a matter of fact, because A is a diagonal matrix, so eigenvalues are just the diagonal entries, which means the eigenvalues of A is just 1, negative 1, negative 2. Because the first condition says eigenvalues of A must have 0 or negative real parts. Now apparently here we have an eigenvalue which is 1, which actually has a positive real parts. So it's not marginally stable. So let's go to the second example, which is x dot t is 0 0 0 0 0 0 and 0 0 negative 1 xt. So again we want to verify is the system marginally stable. Okay. Alright, so according to what we see from the conditions over here, we actually have to find the eigenvalues because eigenvalues of this matrix have to satisfy two properties. Okay, now first compute the eigenvalue. Again, this is the diagonal matrix, so as the eigenvalue is just the diagonal those on the diagonal entries. So we have the eigenvalues of A just 0 0 negative 1. Okay, 3 eigenvalues. So according to the first condition, all the eigenvalues of A must have 0 or negative real parts. So we have 0, 0, negative 1. Yeah, the first condition is met. Now let's move to the second condition. So those eigenvalues with 0 real parts must have the same algebraic multiplicity and geometric multiplicity. Okay, so how many eigenvalues have 0 real parts? We actually have just one of these because they are repeated. So we have 0 and 0. So there's one eigenvalue which appear twice. So they have zero real parts. So this one you can sort of consider this is 0 plus 0j. So this is my real part, this is my imaginary part. They all 0 here. So this is 0 real parts. So here's the definition of the algebraic multiplicity and the geometric multiplicity. Okay, the algebraic multiplicity of a matrix A associated with an eigenvalue lambda I is just the number of the same eigenvalue lambda I. So again, the algebraic multiplicity is just how many of these eigenvalues. You can just interpret it in that way. So geometric multiplicity of a matrix A associated with eigenvalue lambda I is the number of linearly independent eigenvectors for that eigenvalue. Okay, so it means like in order to verify the algebraic multiplicity is pretty straightforward. We just to count how many the same eigenvalues. Of course, we're here talking about those eigenvalues with 0 real part. Okay, so from here we can check the algebraic multiple for eigenvalue 0 is just 2. That's because I have 2 eigenvalues, same eigenvalue which has 0. Okay. All right. So before talking about that one, I want to ask one question, okay, which is if the algebraic multiplicity for eigenvalue, some eigenvalue lambda I 0 is 1, okay? So what is the geometric multiplicity of the eigenvalue for lambda I equals 0? That's also equal to 1, okay? That's must equal to 1, okay? Because one eigenvalue must have at least one of the eigenvector, so which means we have at least one linearly independent eigenvector. And also because my algebraic multiplicity eigenvalue is 1, so there's another property is the algebraic multiplicity must be greater or equal to geometric multiplicity. So if we only have 1, apparently algebraic multiplicity is 1, so the geometric must be equal to or less than 1. And since we already have 1, of course the geometric multiplicity is equal to 1. So actually they are by default. So if you only have 1, the algebraic multiplicity, which this means if my algebraic multiplicity equal to 1, so I must have the geometric multiplicity also equal to 1, which is equal to our algebraic multiplicity, which means if you find the eigenvalues with 0 real parts, you only have one of them. You don't have to verify. That's by default. The algebraic multiplicity must be equal to geometric multiplicity, which must be true. So you only need to care about when those eigenvalues with 0 real parts, which have algebraic multiplicity is greater than 1. Okay. So here is greater is 2, so we need to verify, how many linearly independent eigenvector we have for this eigenvalue, which is 0. Okay. To do that, we just need to compute it, right? Because we have to calculate the eigenvectors. Otherwise, we don't know how many of the linearly independent ones we can find. Okay, now let's verify the geometric multiplicity for eigenvalue lambda I, which is 0. So here, let's assume we have x is x1, x2, x3 is a vector, which is the eigenvector of this eigenvalue matrix A associated with eigenvalue 0. So according to the definition of eigenvector, so the eigenvector associated eigenvalue 0 is just given by A times x equal to lambda times x. So replace x by this x1, x2, x3, A by its definition right over here, the matrix A. And also I have eigenvalue lambda is 0, so this is how I get this equation. Okay, by do the multiplication of these two matrices, so I get the left hand side becomes 0, 0, negative x3, the right hand side is 0, 0, 0. So if I look at this one, so I have x3 must be equal to 0 because they must be equal, right? So x3 is 0. However, my x1, x2, they can be chosen freely, which means it doesn't matter what x1, x2 we select. So this equation is always true, which means this guy is always eigenvector of this matrix associated with the eigenvalue 0. Okay, so, well, we can choose x1 to be 1 because I can choose x1, x2 freely. So I can x1 equals 1, x2 equals 0, so 1, 0, 0 is the eigenvector. Or I can select x2 is 1, x1 is 0, which means 0, 1, 0 is the eigenvector. Okay, so here we can say, hey, 1, 0, 0, 1, 0 are linearly independent. So actually, we can already find the two linearly independent vectors. So, and also if you look at the algebraic multiplicity is must greater equal to geometric multiplicity, you can say, hey, because algebraic is 2, and also I already found a 2 linearly independent vectors, so my geometric multiplicity must be equal to 2. Yeah. So we can say geometric is equal to 2 is equal to algebraic multiplicity. You can also say if you don't know, if you don't, you're not quite sure, you can also verify. You can choose any other x1, x2. It can be written as the weighted sum of these two. Okay, by put on the right weights. So it's just linear weighted sum of these two vectors 1, 0, 0 and 0, 1, 0. Okay, so that's why the geometric multiplicity for lambda y the eigenvalue 0 is 2. Which is equal to the algebraic multiplicity. In other words, we can say, hey, the second condition is also satisfied, which means, yeah, the system is marginally stable. Okay? Now let's take a look at one more example. So this one, we make a very slight change to the original system. The difference here, we just add one term entry over here, which is non-zero. We change it to the original, we have 0 over here, we change it to 1. Okay? So we want to verify the system is marginally stable or not. Okay. Again, we can compute the eigenvalues. Okay, I don't want to go to the details of how to compute the eigenvalues. Just lambda I minus a. You set the determinant to be 0, and you compute that. So we find the solution. The eigenvalues are 0, 0, and -1, which is the same as in the previous case. Okay. So because the eigenvalues have negative or 0 real parts, so the first condition is met. Now we're going to check if those with 0 real parts will satisfy a condition that the algebraic multiplicity is equal to the geometric multiplicity. So this algebraic multiplicity here is 2 because for lambda eigenvalue 0 is 2 because I have 2 repeated eigenvalues of the eigenvalue 0. So the number is 2. Now let's verify the geometric multiplicity for lambda I is equal to 0. Alright. So again, assume here x1, x2, x3, this is vector, this is eigenvector, okay, associated with eigenvalue 0. So I do is a times x, this is a times x equal to lambda times x, right? So when I do the multiplication, so I have x2, 0, negative x3 equal to 0, 0, 0. So here I have x2 is 0, x3 is 0. Okay, so only x1 can be chosen freely. So in the previous case, I have x2 can be chosen, both x1 and x2 can be chosen freely. As you can imagine, so I can select x1 to be 1. Of course, this 1, 0 is eigenvector. So, but I cannot find any other vector that's linearly independent of this guy to be eigenvector of that one, because any other eigenvector, because I can only make this one, the first one to be non-zero, but other one must be equal to 0. So the geometric multiplicity for this guy is just equal to 1. So the geometric multiplicity here is just equal to 1, which is different from the algebraic multiplicity. Okay, in other words, they are different. So we can see here, hey, the system is not marginally stable. Okay. All right. So lastly, we will talk about for the what's the condition for the asymptotic stability. So I mentioned, in the previous one, the condition for the marginal stability is when all eigenvalues of A have negative or 0 real parts, and those with 0 real parts should have the same algebraic multiplicity and geometric multiplicity. Now for the asymptotic stability for the linear system x dot t equal to 8xt, so it is asymptotic stable if and only if all eigenvalues of A have negative real parts. So it's much straightforward. We must have negative real parts. Okay. Alright, it's quite straightforward. If you give me an example here, x dot t is equal to -1, 0, 0, 0, -1, 0, 0, 0, -3. So we want to verify the system is asymptotic stable. We just need to verify the eigenvalue. Make sure the eigenvalues have negative real parts. So negative real parts. Okay. So eigenvalues here, because it is diagonal matrix, so eigenvalues are just the diagonal entries, which are -1, -1, 3, -3. They are negative. So you can say yes, it is asymptotically stable. So the second example gives you x dot t, which is 0, 0, 0, 0, -1, 0, 0, 0, -3. Okay, time xt. This is my linear system. So again, we need to verify to check if it's asymptotically stable. We need to verify the eigenvalues to see if they have negative real parts. Again, because this is a diagonal matrix, so eigenvalues are 0, -1, and -3. Because this one have eigenvalue 0, which does not have negative real parts, so the system is not asymptotically stable. So here we can see, yeah, we want to compute the eigenvalues. We need to compute the eigenvalues here all the time. So it's kind of pretty difficult to figure out if we have a high dimensional system when A is like a 10 by 10 or 8 by 8. So generally, how do we verify if all eigenvalues of A have negative real parts? Okay, for example, I give you a 4 by 4 matrix. This is not a diagonal one. It's very difficult to compute it, to verify that. So if you want to verify the system x dot t equal to A times xt, is asymptotically stable or not? Now we have to compute the eigenvalues of A, okay, which is pretty difficult. Okay, there's one in the undergraduate control class we talk about how to compute this, how to verify if the eigenvalues are all negative or not by using what we call the Rouse test. The idea is we have to write the system in this form, determinant of lambda I minus A. Okay, we set this one to be sort of form like this: A1 times lambda something plus a2 times something, you get a sort of polynomial form of this lambda, and you set it to be 0. Okay, then you sort of can use a Rouse test to verify. Rouse test, what you do is you do the higher order, lower order, all the stuff to verify, right? And then you put all the coefficients you calculate over here in the put in the Rouse array, okay, Rouse array, and you calculate the first Rouse 2 rows of the Rouse array. Actually, you just fill the number from the coefficient of the polynomials, and then the remaining rows you just calculate it by cross-back rules, which is a2 a3 cross minus a1 a4 divided by a2. Okay, the similar this guy, this is what number you get right over here, put it over here right below that, and this guy is the second one is this guy is cross-back, it is a4 a5 minus a3 times 0 divided by a4. So you just put it over here right below the a4. You keep doing that until you reach the last column, last row. Then what you do, you check if the first column changes sign or not. If it doesn't change sign, you can say the system is stable, which means that you have positive and negative real parts, right? Otherwise, if it changes sign, then you have positive eigenvalue. You have the eigenvalue with positive real parts. Okay, so I don't want to talk too much about this one, but if you're interested, you can also check the Rouse test to verify if like the system like this will have negative real parts or not. Okay, so that's all about the internal stability for linear time inference system.